Welcome to this week 7 in this course on machine learning operations. In this week, we will be talking about some of the more boring things associated with machine learning operations. I say boring because most data scientists don't really pay attention to these aspects because they think it's boring. But actually, I would say it's the most interesting if you approach it from a systems engineering perspective. So these are the topics of monitoring, logging, troubleshooting, performance optimizing. And in most cases, when you start looking at what value data science is bringing to the table, you would have to think about these topics, even if you don't like it. Traditionally, it's been the case that these topics were quite heavily IT oriented, meaning that you needed to really understand infrastructure, CPU, memory, hard disks, and things like that in order to, help out in these topics. But with the kind of innovation that's happening in the public cloud, a lot of automation has already been provided to end users of data science models and even the developers of the models. So much so that these automated tools make it extremely easy for us to spin up models and have it be running in really good shape, top shape in production. We're going to focus on a couple of open source tools, which are, I would say, the rubric of pretty much every single production grade machine learning operations, that happens in enterprises outside of the public cloud. And then the hands-on portion of what we will do in this week is going to focus on GCP, continuing from the homework pipeline that we've been asking you to contribute towards every week. So let's get into it. Monitoring and performance optimization. It stems from an understanding of what happens in production, right? When a machine learning model operates in production. So as the course name itself denotes, operations is the majority focus of this course, not machine learning per se. So therefore, the operations that are required in production are the ones that really are the most important. And that's what we're going to, dive deeper into for the rest of this content. There are three pillars to operations. The first is monitoring. The second is observability. And the third is response. Monitoring is when you try to understand, or rather, you try to detect what is actually happening. And here you depend upon matrices, you depend upon logs that the application is providing. Matrices could be things like number of requests received, latency per request, and things like that. And then based on these matrices, there is a sense of what is normal and what is abnormal, which are automatically picked up by the monitoring activity and then alerted to the end user. Observability, on the other hand, is trying to make sense of what has been detected. So it asks the question about, what's going well, which is what's normal behavior, what's not going well, and potentially why. The key word here is potentially because, like with any symptomatic based treatment mechanisms, symptoms are not themselves the root cause, while they are representative of many common root causes. So therefore, what we can do at best with observability is to peer into a system and look at potential candidates of things which are causing the underlying bad behavior, and then try to make sense of it and try to understand that. The third pillar is response, and here we are looking to act on the information that we have obtained since then. So the actions can be of three types. The first is when you look at the alerts that come in which are denoting something is seriously wrong, and you treat it like an incident that needs to be resolved immediately. So the example could be that the machine learning model is running super slow, so much so that it's not usable at all. In which case, the alert comes to you, and then you take a call that the model has been, historically running on a CPU. Maybe that's not good enough. So therefore, let me take care of this incident by upgrading the model to use GPUs. Right? That's one type of action. The other type of action is where you don't know what is the, way to resolve the problem. So you end up doing what's called as troubleshooting by debugging further into the code, by looking at various aspects of production runs, logs, matrices, etc., and then try to figure out what could be going wrong. That entire activity is troubleshooting. The third angle is optimization, where you focus on what needs to happen for the model to scale gracefully to the extent of volume and velocity that's been provided to it. So that's optimization. The three pillars actually apply at two different layers that are of interest to us in this course. One is at the layer of the machine learning models themselves, and the second is the underlying system on which the models run. So the models and what can we do with respect to operations on the models themselves? We will focus a bit on that in a later week. I think it's week 9 in the course. But for today, or rather for this week's content, we will predominantly focus on the systems angle of it. And that's where, like I said, there's a lot of automation that's available to us. We make the best use of it and then get our problem solved. Systems monitoring comes down to 4 different aspects of what constitutes a healthy functional system. The first is the latency has to be acceptable. Second is the ability of the system to handle a reasonable amount of concurrency. No system can handle infinite concurrency by itself without requiring external help. Like, for instance, the help could be improving the system, giving more resources to the system, or planning ahead of time to see what more can be done to control for the workload that comes in. But a reasonable amount of concurrency is something that usually business sits with the data scientist or the machine learning engineer and arrives at a consensus, and then that gets engineered. The third is resource utilization. What's reasonable and how many resources are being utilized for a typical production run. And the last part is API health, because these are machine learning models we're talking about, and these are containerized models. So the APIs that they provide, which allow us to execute predictions, what's the health of those APIs? Can I continue to rely upon them for the next 1 week of workload? If not, are there early signs of degradation, in which case do I need to do something about it? So systems monitoring broadly deals with these 4 angles. So if you get these 4 angles right, you typically have a well-functioning ML system. So what's latency monitoring? It's the ability to look at various aspects of performance, but from the lens of latency, from the lens of how long a model prediction takes, a model inference takes. So here we've got a few, interesting matrices to measure. That's typically, good enough for arriving at a coverage of model health. The first is response time, and specifically, instead of raw response times by themselves, we are interested in the percentiles. And even more specifically, since we don't want response times to be too large, we are interested in continuously monitoring and tracking the higher end of the percentiles, which means the higher end of the response time spectrum. So notice that for a typical model execution, you might have a range of response times. Like, let's say you run the model by itself, it takes about 100 milliseconds. You run the model along with 10 other models in the same machine, 100 milliseconds becomes like 150, 200 milliseconds. And then the same machine which is hosting 10 models now is receiving hundreds of connections. So the 200 milliseconds becomes 1 second. So maybe that's all perfectly natural and you're okay with it. In which case, you've got to define what the normal is, right? So in the scenario where there's a lot of load, a lot of models running, 1 second could be the norm. In which case, the typical model execution being 1 second is not problematic because that's within the range of expectations. But if the response time goes up to 10 seconds instead of 1 second, then probably you need to be alerted about it, and you might want to take some action on that. And if you look at then the spectrum of response time for all the executions of the model, it could range from 1 second to 5 seconds to 10 seconds, but the typical range being within 1 second, which means the 5 seconds and the 10 seconds will show up as the value if you sort the entire response times on a scale and then pick the max value or, closer to the max value. That's why the percentiles that are of interest to us are on the higher end of the spectrum. We're interested in the 95th percentile, we're interested in the 99th percentile, and performance optimization typically focuses on reducing this value. Because if you reduce the 99th percentile to within the range of expectations we have, that automatically makes the typical execution, which is the median execution value, the 50th percentile value, lesser than that. And therefore, it means that for the majority of the executions that happen for this model, it's within reasonable latency. So that's why the percentiles at the higher end of the spectrum are things that you track. The other interesting metric that could be tracked for certain types of models is what's called as time to first byte. So let's say it's a chat completion model using LLMs. You might or might not be using RAGs as well. But the point is, in those kinds of models, the time taken to respond is not just with respect to the complete response, which obviously would take time because it's got, let's say, various types of reasoning, various types of analysis or tooling that needs to execute for answering your question. But the latency is measurable in terms of what's the first byte and how long did that take to come. Because for the user experience, like for instance, me sitting in front of ChatGPT, the first, line shows up, and then I get hooked on to that answer. But until the point that the first line shows up, let's say that the ChatGPT window just keeps saying, searching the web or gathering information or analyzing the question, and that goes on for a long time while it builds up the answer in the back end. I might have lost patience. I might have executed something else by that time. So the time to first byte is a very important metric for certain types of models, especially the LLM type of models. The third angle is obviously model inference time. So a typical response time is going to be comprised of multiple steps. Like you have the model the execution by itself, but you also have the data processing, which is required for converting the input data into a form that the model understands. And then you have interpretation on top of the model output. So taking the inference and then attaching a particular meaning to it semantically, and then responding back to the API. At times, you might also have to do like dependent workflows. So all of that put together is the response time. While that's, of course, meaningful and informative, what's also going to be pretty useful for you to understand is the time taken for the inference itself, the inference step specifically. So if you can split it up from the total request time or the total response time, that's even better. But at the minimum, being able to trace the inference and the time that it takes is going to be part and parcel of what constitutes a healthy ML system. So what tools are available to do this? The first and most interesting and comprehensive set of tools is what's called as the observability stack. We're going to spend some time on this a little later in this week's contents. But for now, let me just summarize it for you. Prometheus is an open source metrics collection tool, and Grafana goes hand in hand with Prometheus, which is an open source UI or a dashboarding tool for matrices. So both of these are complementary, and it's great to use because it's open source. You can set it up on any machines, any configurations that you like. And if you also like directly purchasing from them, you can get that from their own respective cloud. So a lot of options, a lot of flexibility. But the good part is it's Apache licensed 100% open source, so you can use it in any way that you like without having to pay anybody else any money. So you can do things like HTTP latency, histograms, you can do percentiles, computations, etc. Now, for understanding what's happening with a specific model invocation, which might be requiring multiple different hops because the models could have submodels, etc., you need to do what's called as tracing. And for tracing, there are specific tools available. Jaeger is one such example. OpenTelemetry is another. In fact, in our example later this week, we will take a look at the OpenTelemetry SDK. And last but not the least is the extent of help in latency monitoring that you can provide from within the app itself. So far, we've used Fast API for Dockerizing the model and and exposing it as an API. So you can actually add a couple of other elements to that particular program to make it easy for monitoring latency. We'll take a look at some examples a little later. So the Fast API instrumentation stems from an understanding of Fast API that's important for you. We've actually been very casual users of Fast API so far in this course. So in this week's contents, we will dive deeper into some of the nuances of Fast API as well. So one of the interesting aspects of how Fast API looks at handling some of these features is by introducing this concept of a middleware. So a middleware is a layer that sits between the front end and the back end. So that's very simply put. In the context of the machine learning model, what is the front end? The front end is actually the API, right? In our case, it's the Predict API. That's what we Dockerized. In the back end is the model execution that's happening on CPUs within the Python process. The middleware is what happens to the requests that come to this particular model through the protocols. In our case, it's the HTTP protocol. So at that time, can you deal with the requests and do some interesting things related to operations by dealing with it? So the reason it's called middleware is because it's agnostic to what's happening in terms of content or payload, and therefore the functional logic associated with that particular endpoint or REST endpoint. So in this case, the Predict endpoint is not something that the middleware needs to know about beyond the fact that it's actually using HTTP protocol. The fact that I'm using an ML model within it, etc., all of that is details that is abstracted away at that layer of protocol handling. So what this particular example shows you is for every request that comes in for Predict or anything else, let's handle it at the middleware layer so that we are not affected by what's happening within the functional elements of the application. So I'm going to deal with it as an HTTP request and then log the time. So basically get the start time, then do the actual request itself. And when I do the actual request, I execute a special command called as call next and give it the request. The call next basically is a reference to the actual endpoint that's being requested in that request. Like for instance, in our case, it's Predict. So before Predict gets invoked, the middleware gets invoked because it's the middleware at the end of the day. The middleware goes to this logic, and then the await call next will then go do the call to the Predict, and the Predict will return back with an answer. That is the response. The await makes it synchronous. Once the response is available, I can look at the time again and do a diff between the time before versus the time now. That becomes the duration or latency. And then that gets logged as the response time, and then the response gets returned. So as you can imagine, the call next will work with any endpoint. So you could have called some other endpoint like aliveness or readiness, and then this entire process will still apply. So this middleware instrumentation is quite useful. It's something you can layer on top of any of your programs, not just ML. So you can extend this implementation to add other kinds of details. In this case, I've just done the latency calculation as a simple end time minus start time. You could also do other matrices. You could do logs, and you could also start sending matrices to Prometheus. Remember, Prometheus is a metrics collection tool. Okay, so that was latency handling. Let's talk about concurrency handling as the next step. So here we're interested in tracking and testing how many requests of the model invocation are coming in simultaneously and how many of them are getting handled concurrently, simultaneously. When I say getting handled, I mean successfully getting handled, not getting queued up, not getting bottlenecked because resources are not available, etc. So if you can successfully handle a reasonable amount of concurrency, you know that the machine learning system is healthy. So what are the strategies for ensuring that concurrency can be handled in a way that's graceful? One of the first is something that we've been following all this while, which is asynchronous programming. So if you remember, with FastAPI, we used UVCon, which is the ASGI compatible version of Python's web framework functionality. So ASGI stood for Asynchronous Server Gateway Interface, which is basically an asynchronous framework for executing REST requests and then getting back responses from it. So the advantage with the asynchronous frameworks is that you're not waiting for the execution to finish, and therefore you're not holding on to resources which are potentially in short supply. Like for instance, network sockets. So when you make a HTTP request, you're actually making a request over a temporary socket, which lives for the duration of that particular request. So if you make a synchronous request, then you've got to wait for the duration of the execution, and for that duration of the execution, that temporary socket is taken up. So the number of temporary sockets available are finite. So you can't handle more than a certain concurrency if you keep doing these synchronous operations. So better to use asynchronous frameworks. The second angle of concurrency monitoring is that actively monitor number of threads and number of processes, especially threads per process. That helps you get a very good sense of the actual CPU core utilization. And CPU cores and memory become the typical bottleneck when concurrency is high. So keep that in mind. The third way in which you can deal with concurrency is by defining connection limits, which are reasonable. And these limits then issue some kind of an upper bound on how many concurrent transactions or requests can happen at the same time, beyond which the requests either get queued up so that they can wait in the queue for their turn, or they get denied because the server is unavailable or server is busy, in which case they can be tried again at a later point in time. So setting these connection limits in the reverse proxy, basically the load balancer, is the best approach. That way you can limit the extent of damage caused by too many concurrent connections on the entire system. You limit it to the load balancer stage itself. So what tools are available for concurrency benchmarking? Apache Benchmark, Work or WRK, and Locust are three very good examples. Again, open source, again, it's easy to use. Locust is in particular quite useful for simulating load with custom scenarios, which means, let's say you want a range of different types of requests that come in, not just predict on a model. Then you can use Locust to actually simulate that. But for our purposes, because we have a predict API and not too much else in terms of complexity, we can directly use a simple, concurrency tool like Work to spin up a whole bunch of different connections and then do a performance benchmark. So here's an example. I've executed the command against a particular model endpoint, which is predict. And this endpoint is hosted on GKE. As an example, it could be Docker, but GKE obviously is better for production. And then what it's doing is it's executing 4 threads in parallel, 100 concurrent requests, and the duration of the entire test is 30 seconds. So let's say that each request takes about a second to finish. So as and when a request is finished, another request gets spun up. So therefore, at any point in time, 100 concurrent connections are always happening. The duration is 30 seconds, meaning I run this test for an elapsed time of 30 seconds. So if your machine learning model is operating really slowly, then the latency associated with each model execution could be very high, in which case I may not be able to get through as many number of requests in that 30-second window. As opposed to, let's say, a very fast executing model, which has much better throughput. So the throughput differences will show up in this kind of a test if your latency is actually very high. So that's concurrency handling. Next, let's talk about CPU and memory utilization. So here, I'm interested in monitoring the resources themselves and specifically the CPU and memory, because those typically get bottlenecked quite easily, and how efficiently these are getting used by the system. So here you're looking to track CPU spikes, um, especially for deep learning models which have metric style operations. If you don't have GPUs, then you're going to see that impact on the CPU quite drastically. Then memory leaks or usage that grows over a period of time. Now, with Python-based models, you may not see that often, but it really depends on the libraries that you import, right? That are dependent um, from your model. So those libraries in turn might be using certain structures. They might be implemented using certain algorithms or languages, which make the problem of memory leak quite intensive. So keep a watch on that. And last but not the least is, of course, GPU usage, because what is conventionally the logic is that most GPU-based algorithms are not multi-threadable, right, so to speak. They are single-threaded, which means they operate on one GPU uh, per process. And then if you've got multiple GPUs, then it does parallelization at a process level. So then how is the GPU being used? Was it waiting for disk half the time? In which case it's an underutilization of the expensive GPU chip itself, etc. So those are all, resource utilization topics to think about. The tools here are many. It really depends on which infrastructure you use. Let's assume we use Docker and Kubernetes only. Docker for packaging and building and testing, and Kubernetes for hosting it in production. In which case, you can use Docker stacks as a command for understanding what's happening in the container in the testing environment, and then use various types of Kubernetes provided executions, logs, or Prometheus matrices to understand what's happening for a specific type of container or pod within that Kubernetes cluster. So the example from Docker stacks will look something like this. A particular container takes 65% memory, a point-in-time snapshot, by the way. So it's not representative of the lifetime of the model. It's point in time in that specific instance when you executed this command. And the memory usage is 512 MB versus the allotted limit of 2 GB. And the last of the topics related to systems monitoring is API health. So here you're interested in looking at the total request volume and how many resulted in errors. So one of the useful metrics here is throughput. So the more throughput of successful requests you have, the more optimized is your system. You could have a high throughput and not have many of them be successful, in which case something is wrong, like there could be bugs in the platform. Or you could have low throughput and all of them be successful, in which case probably you're handling everything correctly, but then you're spending too much time or resources to do that. Therefore, you don't have enough time to process more. So a high throughput of good executions is something that's desirable. The second angle is, the success or failure of responses. Like, so here you've got to understand HTTP error codes, because these are RESTful APIs. They ride on top of the HTTP protocol. So 200, for instance, as a response code is okay, which means it's a good execution. Anything else typically indicates something is wrong. Like a 400 is typically for internal server errors. 500 is, has its own connotation, etc. So you've got to be able to segregate between the two to understand what is happening. Timeouts and retries are also usually an early indicator of, actually it's a lagging indicator of resource contention. So if you got a query timing out, it typically means that there isn't enough resource to execute that particular query or prediction. Retries typically indicates that the underlying resource is having problems with being stable, and therefore it's getting restarted, and therefore the entire query or the workload is getting retried. So that's also an indication that something's wrong potentially. Then the last two angles here are, very interesting and, simple ways in which you can keep track of your model health. The two, topics here are called as liveness and readiness. Liveness just refers to the fact that the model is running. Let's say the model goes down for some reason. How do you figure that out? It shouldn't be that you're executing a prediction request and then that's returning with a 400 error saying server is unavailable. In most cases, it's more important that you are able to, identify that the server is down much earlier than the user telling you the server is down. So that's what the liveness check does. It helps you, continuously check a particular container or the service that it's live. And if it's not, then it takes some actions based on that. One of the actions it takes is it just restarts the entire cluster. So which could be quite interesting. Readiness, on the other hand, is not about whether the model is live and running, but whether the model is loaded at all in the first place, and all the dependencies associated with prediction or doing the prediction process, are they satisfied? So is the model loaded and ready to serve? And the ready to serve corresponds to these dependencies. So that's readiness. For deep learning models, readiness is an important parameter because the time it takes for loading a model with large weights is significant. So you could have started the process, let's say at 9 a.m. It might be still going on by the time it's 10 a.m. because the foundational model is that large. So I don't want to execute any request in that time period from 9 to 10 because the model as itself is not ready. So readiness is actually a pretty interesting, behavioral outcome, I should say, that we are interested in tracking. Okay, what kind of tools are usable for this? So for liveness and readiness, it's advantageous to expose separate endpoints. Like you can call them health, or you can call them ready or live check or ready check, etc. But think of it as separate endpoints, which are get endpoints, and they in turn relay the state of the current state of the app and ensure that the downstream user is aware of what to expect when the app is getting used again. So liveness readiness has standalone endpoints that need to be supported by the deployment itself. Then Prometheus and Grafana, we spoke about it before. If you use them in conjunction for API health, it's very powerful, especially Grafana dashboards. Then if you integrate health checks with the containers, container layer, in this case Kubernetes on managed Google Cloud instances, then it makes it very easy for you to have an integrated view of what happens for an API, including at the pod level, at the container level, at the node level, and of course at the API level itself. And then last but not the least, especially when you're consuming services or exposing services for others to consume, then it's best to think about having one simple way to monitor uptime, so that you keep track of how long that service has been up and running. So there are many uptime tracking agents like Uptime Robo, PingDom, or even custom Prometheus jobs that can get the job done. Okay, so I'll pause here. In the next part of this video, we'll take a look at the modern observability stack. Thanks.